We take another example and we want to find the local extrema of the function fxy. This is 3y square minus 2y cube minus 3x square plus xy. So this function is also polynomial function in x and polynomial function in y. So it means its derivative is differentiable in all the plane xy. So its domain is the plane xy. So I just find first the critical points. First I find here the critical points. To find critical points, I need first derivative test, and the first derivative tests are f of x. Now my f of x is y is constant. We are having here minus 6x plus 6y, and we put this equal to 0. And then we find f of y, taking x as constant, get here 6y minus 6y square plus 6x is equal to 0. So this is my equation 1. And this is equation 2. This is nonlinear equation. Then we want to find the value of x and y. From equation 1, we can have minus 6x plus 6y equal to 0. Or we can write here 6x is equal to 6y. Or we say x is equal to y. So I can change x equal to y or y equal to x. The second equation is 6y minus 6y square plus 6x equal to 0. I change x by y. So that gives me 6x, 6y minus 6 y square minus plus 6x equal to 0, and in place of x I will get here y because I change x by y. Now I am having here 12y minus 6y square equal to 0. I factorize this one and I'll get here 6y, I take common and get here 2 minus y equal to 0, and that gives me two values, y equal to 0, y is equal to 0, and the second value is y equal to 2. So I get here two values of y equal to 2, and then I use here this equation 3 to find the value of x. So that give me x equal to 0 by using number 3 and y equal to 2. So I say here my critical points are there in the domain of the function, and say both are the critical points are 0, 0 and 2, 2. Here we are having here x equal to 2, we put the value of y and get x equal to 2. So my points are 0, 0. I get two critical points. At these two critical points, I can have a saddle point, I can have a local extrema. Now to check that one, second is I have to find the discriminant. Discriminant is my dxy is equal to f of xx, f of yy minus fxxy whole square. So I go above and I find my second derivative of my function which I have defined here. So I can find here my second derivative. I have here the first derivative, f of x is minus 6x plus 6y. So f of x is minus 6. And f of xy is equal to 6. And then here I am having here the value here f of y. F of y is equal to 6y minus 6y square plus 6x. Now I find here f of yy is 6 minus 12. This is my f of yy. Now I find my discriminant. That means I multiply f of xx and f of yy. That's minus 6 into 6 minus 12. So I can write here this equal to minus 6 into 6 minus 12. Then minus, we are having a 6 minus 12y. Here is minus 6 minus 12y, 12y, and then minus f of yy. F of yy is xy is 6, so get minus 36. So I simplify this one, I'll get here multiply by 6 is minus 36 plus 72y minus 36. So that gives me here 72y minus 72. This is my discriminant dxy. Now number 3, I now used my second derivative test to find the local extrema or saddle point. Here I use this one. Now I take the critical point 0, 0. I have to my AB is 0, 0, and find my discriminant at point AB at point 0, 0 is equal to minus 72, which is less than 0. This implies a saddle point. And if I just find the value of this one, f of 0, 0, then my f of 0, 0 is equal to 0. So this is my saddle point and the value of the function at that one. Now this is my here number 1. Number 2, I take the second critical point. The second critical point is my AB is equal to 2, 2. Now I find here the value of the discriminant d at point 2, 2. I put here x equal to y equal to, I have 72 into 2 minus 72 is equal to 144 minus 72 is equal to plus 72 is bigger than 0. This means, this implies there is local extrema. There is local extrema because we are having the discriminant bigger than 0. Now I take secondary test, I take f of xx or f of yy. So I just take f of xx and find the value of this one at point 2, 2. So we get here the value of this one at the point 2 and 2, which see it here, we have secondary test, the value of this one at the point 2, 2. Here f of xx is minus 6, remain minus 6. This remain minus 6, and this is here less than 0. This implies there is local maxima at this point. Now you can find the value of the function at the point f of 2, 2 is 8. So this is the local extrema of the function. We get here the saddle point and local extrema. I want to show you this in a graph, and I can have here the graph of the same function, and we having this as you can see it here is going below minimum, and here is going above, and this point is the saddle point, and this point is point 2, 2. This point is this point here is point, we say this is our maxima minima, this is our point, the point f of 2, 2, and the value of f2 was 8, and here is the saddle point, and saddle point f of 0, 0, and the value of this one is equal to 0. This was my saddle point, and this point was our local maxima. So you can see here in the picture also, it's not very simple one, but we are having here the idea that this is giving me this, the point is my saddle point and this point be local maxima. I'm going to take another example. Here the function is not given directly, but we have to develop the function, and then we have to see that what is the requirement of that one. Find the minimum distance between the origin and the surface. So we want to find the minimum distance. Given is the idea that we are having surface and we are having the origin. What? So the distance, we have the distance formula between the 2 points. We say this point is on the surface and the point is the origin. We can find this distance between these two, and we see because we can have different points on the surface, so we can see which point at which place we get the minimum distance. So for that is the question of this one, that we minimize the distance. So I will take the distance formula. We are having this d is equal to root of x minus 0 square plus y minus 0 square plus z minus 0 square. So we say let x p x y be a point on the surface. Distance of the point to the origin given by d equal to x square plus y square plus z square under the root. If I take d square, it will be x square plus y square z square. If d square is minimum, it means the d is also minimum. So I take the d square equal to the function of x, y, z. We say function of x, y, z is x square plus y square plus z square. Then we are discussing always the function of two variables. Now here there are three variables, but we are given here the condition that this must be on a particular surface. That surface given to us, z square is equal to x square y minus 4. So we replace for z square with x square y minus 4. So we get equation find two variables. So get fxy is equal to x square plus y square plus x square y minus 4. Now here is our regular question which we are solving before. This one we find here the critical points, and then we use these critical points to find the discriminant, and the second derivative we use to find the maximum minima.